guest lecture seminar series under the aegis of Click Chemistry Research and Studies, Amity University. It's my proud privilege and honor to welcome and introduce a person who is pioneer in the field of organic chemistry, Professor B.C. Ranu. He's sitting here. I started my career from cultivation of science and had the opportunity to meet him and visit his lab. So let me introduce him. Short. Not yes, very short. Okay. Professor Ranu's career at ISES was marked by steady progression and leadership. He rose to the position of senior professor in 2006 and served as head of the Department of Organic Chemistry from 2003 to 2008. After retiring from his regular position in 2011, he continues his scientific pursuits as J.C. Bose Fellow, DST Government of India, and Indian National Science Academy Senior Scientist, and currently INSA Honorary Scientist with the same department. In 2022, he accepted the role of chairman of the Laboratory of Advanced Materials, Green Synthesis and Biotechnology at the Ural Federal University at Russian Federation, where he spent several months each year supervising ongoing projects. This assignment continued till December 2024 and produced several research papers and patents. Professor Ranu's contribution to the field have earned him numerous accolades, including Fellowship of West Bengal Academy of Science and Technology in the year 1994, Fellowship of Indian Academy of Science, Bangalore, 1995, Fellowship of Indian National Science Academy, New Delhi, 2009, Narsimhan Award, 1993, Chemical Research Society of Indian Bronze Medal in 2001, J.C. Bose Fellowship from DST Government of India, 2009, Chemical Research Society of India Silver Medal, 2010, J.C. Ghosh Memorial Award of Indian Chemical Society, 2018. He has held visiting professors at international institutions and has been an active member of various national and international committees, including IUPAC and the Green Chemistry Task Force, Government of India. Professor Ranu's research has stimulated great interest and inspiration within the global chemical community. His work has been widely recognized, leading to the invitation to deliver several keynote, plenary, and invited lectures at symposium worldwide. His enduring enthusiasm for chemistry continues to drive innovation and excellence in the field. He has co-authored book Ball Milling Towards Green Synthesis, Applications, Projects, Challenges, published by Royal Society of Chemistry in 2015, and has been highly appreciated by the practicing chemist. With all these words, because it will take a long time to introduce all his accolades and honors. So with all this, I request Professor Ranu sir to take the dais and give his talk. Let us give a big round of applause for him.
Not working. Okay, anyway. Thank you, our beloved Monalisha, Professor Monalisha Mukherjee here, for inviting me and giving me this wrong introduction. Okay. Yeah, I met her, after she left our department, I met her sometime few years back in Pune. And then I met her another time, and this time in Bhatinda. I saw her, and then really I was happy to see her in this position and here. And for any teacher, it's the pride that when students have got high positions. So it's the same with me. And I also, I'm very happy to get this opportunity to visit Amity, here your department, colleagues and you. So it's really, I'm excited. Okay. So, as you see, what I'm talking today, that's functionalization of CH bonds, a green concept, challenge and measures. Okay, just a minute. Okay. Before coming to the main topic, let me say that I retired in 2013, and then I continued as an institute to the active group until 2020. So 2020, I surrendered my lab. So last 5 years, I don't have any active research group. So whatever I will tell, that's about little older work, but what I want to share my experience in this my almost 40 years journey of this research career. Okay. Just before that, I would like to tell a little about my introduction to research. By training, I got exposure in natural product synthesis, both in PhD and postdoc. So when I came back in 1985 to cultivation of science as a researcher, always in my mind is coming that total synthesis and all the things. That time I have only one student. So I started that and did some work towards that, synthesis of, semi-synthesis of molecules, published one paper in ChemCom and JOC in 1987 after joining 85, fine. But I realized that doing natural product synthesis with one or two students, then 87 I got another student. So two students and myself also working that time. So with two hands, you cannot continue natural product synthesis with the facility we had that time in ISS. We didn't have NMR that time. So whatever you need after making one compound, then what you'll do, you have to go to some other place to get the NMR. Research cannot go in that way. So I thought that to survive on this, I can, if I continue on natural product synthesis, I cannot. So I then switched to development of green synthetic process, although green term is not that coined when I started. So to say environment friendly synthetic procedure catalyst. That was my turning point from 89. So in 90 I published the first paper, that is which is now this reaction on surface mediated surface without solvent, which is still hot topic. Whenever doing some reaction without solvent on surface, that's a good thing for the industry and things. So I started my work on the green chemistry, say from 19, and since then, whatever I did, that is always a green stint. So whatever I did, many projects I have done. I'm not talking about this. And this topic, that is my one of the hot topic during 2010 or so. If you look at the literature in 2010-11, that time, that every big chemist are doing on CH activation. CH activation is a big thing. Okay. So, and that's a green concept. I'm coming to that. So in that way, and because green, that green also, my perception is little different from the bookish perception, what you find in book. So what is green chemistry? Let me talk about 2-3 minutes about green chemistry, then I come to my topic. Okay. So what is green chemistry? So my perception is nature's chemistry. So what is nature's chemistry? Okay. That's my really, this synthesis, I love it. And that's my, you can say that's, it's my always inspiration. And my whole chemistry is based on that. That is the photosynthesis. You know it's the photosynthesis, you know from class 6. But in the other perspective, that is a reaction, reaction in the plants and all the things. But if you look at the reaction, analyze the reaction. This reaction is the reaction of carbon dioxide and water to produce glucose and oxygen. But look at the starting material, they are all innocent, abundant, cheap, okay, fine. And the product, look at the glucose is a very, very useful material. And the oxygen, I did not talk about what is the importance of oxygen. And plants are doing this reaction all the time. So you know the importance of this particular reaction. But for a chemistry angle, if you look at this reaction, only this reaction, how important this for this. So what you learned, I'm coming. Use of inexpensive, abundant, non-toxic chemicals for your reaction. Okay, you did not memorize green chemistry, you do not know what is green chemistry. Look at this thing and then analyze. In presence of chlorophyll, catalyst and sunlight. Look at this, no solvent. Only catalyst, chlorophyll and sunlight. Okay. no heating, nothing. You are getting these products. So again, for your reaction, if you use some catalyst which is non-toxic, no solvent or non-toxic solvent, and in sunlight, if you can do without using any electricity, that is ideal. That is ideal. So that is the ideal condition for green chemistry, or this is only green synthesis. You don't look about 12 principles. You don't look at 14 principles. Look at the thing. I will derive all the principles from this. Okay, nothing else. That's all. So that was my, say, you can say, the mantra from starting from my research. That's okay. Photosynthesis. Now let us look at little this. What we learned from here. What I took, same thing. Use of reactants that are non-hazardous and easily available. Fine. Do your chemistry in that way. Generation of products which are non-toxic and useful. Fine. Use of solvents that are environment friendly or no solvent. That gives my first reaction, the green synthesis without any solvent, reaction without solvent. Okay. Then use of catalysts that are non-toxic and inexpensive. And use of sunlight if possible and reaction room temperature. They're the ideal condition. If you can do all the things, that's great, but not possible. You cannot follow all the things only nature can do. We cannot do everything. That's what nature can do. So, and generation of no waste, very important point these days for industry, for generation of no waste. Okay. So these are the things you derive from this photosynthesis. Okay. And if you look at the principles, they are the same. I will come to next thing. And I was a member of IUPAC Cameron committee for almost more than 12 years. So that time when I put all these things, the chairman asked me to, why don't you write a article on Chemistry Chair International? So I wrote an article on Chemistry Chair International in 2021 is published. That is learning green chemistry and its principles from nature's process and development of green procedures mimicking nature. And that article is widely appreciated, and it's really that how you can make chemistry just mimicking nature or photosynthesis. Okay. Now, if you come to the book Green Chemistry Principles, what is that? Green chemistry, environment friendly. Look at photosynthesis. Just look at this, and in your mind, backmind the photosynthesis. So this is environment friendly, simple. Nothing can be simple than photosynthesis. Sustainable, it's sustainable. Atom efficient, all atoms are used. Economical, very good. Safe, non-toxic, and avoid waste. So whatever all these things about green chemistry in book, you can learn everything from the photosynthesis, right? So if you know photosynthesis, which is very simple, very thing, your knowledge of green chemistry is over. That's my perception. Okay. With that, then I started my research, and here I took the CH functionalization. I will come to that. Before that, so how can we implement green philosophy? These things. One thing, this is my things, and nothing else. One is by using green tools like solvent, solventless, energy, and technique. I will give one example of technique, and mainly I will devote my time for design of green strategy today. By design of green strategy, that's one of the things. That's one of the objectives or principles that I will do. And that thing not talk about today, green reagents and catalysts, I will not come to them. Okay. But this green technique, I will give one example. Again, because it's a click chemistry institute. Again, that's this reaction developed by us. If you see that, click reaction, the Nobel Prize winning reaction. And it is actually the reaction of alkyne and alkyl azide, right? Or aryl azide. So here, what is our objective and innovation is that instead of making the azide separate state, if you can do it one step, that's also, if you look at the objective of click reaction, that's the do it academic way, one pot, simple, without solvent. All these things are objective of click reaction, not only one reaction. If you look at the things, follow everything here, that we used an halide, aryl halide, sodium azide in one pot and alkyne. If you have to bring the azide, you need another pot, another good. So what we did, without handling azides, without giving one step, another step, so we did alkyl azide, sodium azide and alkyne in one step, and copper alumina That's the catalyst we developed by us, and we get good revenue. We have many papers on this now, and now it's marketed by Orlich. So Sukoland did it anyway. So copper alumina, our catalyst, and under ball milling. This is under ball milling. You say that 600 rpm, 6 balls, 60 minutes. So this reaction without any solvent, without any solvent, without any other reagent, and copper alumina is recyclable. It can be recycled enormous time, 10 times, 12 times, no problem. And this reaction, the example here, look at the yield here, yield is very high. And about the purification, after the reaction is over, you take the whole mass, the reaction is done, take the whole mass, put a small column with a plug, elute with ethanol, just wash with ethanol, evaporate the ethanol. Most of the time you will get a solid product. No purification, nothing. Or if you get liquid, just liquid, you can give microdistill if you want. Otherwise, most of liquids are also thing. So, but if you look at the technical, that this procedure is very simple and green in many ways, right? No solvent used, no solvent used in purification, high economy, and very simple thing. So all these things, and what I'm telling that after publication of this result, I got an invitation from DRDO, Pune. They said that just we had nothing said. They said that we are inviting you for a talk. Many times I got invitations, so I went there. So when I talked about the things, then said that because we invited you to know details of this reaction. Here they are saying that they use this triazole moiety for explosive because it's a high content of nitrogen. Explosive means when it's a high content, it's trinitotoluene or so, high content of nitrogen. So there's a high content of nitrogen. They have some substitution and all the things. They are interested in this molecule also. So they took the details of me, all the things, and they said they used it, and afterwards they wrote to me that we are using your method for making triazole. So even if you look at it, that's one of the simplest methods published so far. That is for making triazoles. Okay. So they start with that. Now coming to my three check. Okay. As I told already, that is avoiding the handling of hazardous and toxic azide, solvent-free procedure. Very important. Use of environment-friendly ethanol for isolation of the product. That's very nice. For ball milling reaction, I'm not talking ball milling today, but many times I talk about ball milling. So ball milling is one of the main thing is that most of the time you don't need any solvent, and purification is very simple without any solvent, and these products are good. I mean high purity. So ball milling is one of the say favorite techniques in all the labs. And in Germany, many industries are using ball milling as a regular method for their product. So they increase the overall yield by decreasing number of steps and catalyst recycle. That's all those things then correspond to green synthesis and click reaction. Okay. Now coming to CH activation. Just coming for the students that what is CH activation? Why that is necessary? Okay. If you have to make this functional group, what is the classical procedure? You need one pre-functionalization here, right? And then a nucleophilic displacement, you can get this compound. That is the classical traditional procedure. But in this case again, this does not follow the green principles that you are losing two groups. I will come to the practical example. That's one thing. So the people are thinking that how to avoid that. Okay. Then they found that, okay, if I put a directing group, mainly consisting some nitrogen compounds, pyridine, purine, or whatever amide or so, then with the help of a metal, usually palladium, you can activate one of the positions, ortho positions, sometimes meta, para, whatever. It's like this, something like this. So you can activate this position, you can then substitute. So that is activation. CH activation means one of the inner CH bond is activated with the help of a metal and with an adjacent, or this is a nitrogen moiety or some functional, which is called directing group. That is actually the CH activation. Okay. Now, if you come to a real example, this is a famous Suzuki reaction. If you look at the thing, the Suzuki reaction actually is making a carbon-carbon bond, nothing else. So making this carbon-carbon bond, what you are here, you are losing a BO is to, you are looking Br. So that's not at all atomic. So it's not, in that way, it's not green. It's a wide applicability. That's why he got Nobel Prize. But if you look at the green angle, this is not green. So that comes the concept CH activation. Look at the same type of molecule. You have this hydrogen here, inert, I mean CH not is functionalized, inner CH bond, and you have, because of this thing, this bond is activated in presence of palladium. And then if you have some aldehyde here like this, you can get same carbon-carbon bond. So you are constructing a carbon-carbon bond through CH activation only with the loss of 2 hydrogen. If you compare this and this, that is much greener. This is just greener. That's why the concept wise, CH activation is a green concept. Okay. Now I am coming. What about the, as I told you the other day, I was talking about many sense that you do the reaction in water. Fine, you are claiming the green. After the reaction is over, you add tons of solvent to extract it. Then another ton of solvent just to purify it. Did you call it green? No. So the concept is not only thing. Concept is first step. Then implementation. Then whether you have to talk about, whenever you talk about the green, that's why now green metrics are there. Whenever you publish in a green chemistry or good paper in any journal, they will ask for a green matrix, that eco scale, E factor, which tells you that how green your method is, how much solvent. If you use lots of solvent, E factor your will be high, right? So that's a thing that you have to consider whether really it's green. So I'm coming now implementation. Okay. So when CH activation came, if you look at the literature, I mean almost 90% papers use palladium catalyst. Almost all, if you look at the papers and all the things. But palladium is not good. I'm coming at that point. Okay. Now, so when at 2010, 11, 13, so we started the work on CH activation. And then I'll show only a couple of examples, although I have many. So one is CH nitration of arenes by palladium catalysis. And nitro compounds, as you know, many nitro compounds are marketed drugs. The many marketed drugs contains a nitro compound. So it's very important functionality. Okay. Now this reaction is in my lab. Okay. If you look at the thing here, this is the activating group, directing group, and here we have this position, and we have made the nitration here at this position. It's tertiary butyl nitrate. Again, look at my things. Usually use metal nitrate, sodium nitrate or sodium nitrate, something like that. But we use tertiary butyl nitrate again because less toxic than metal nitrite. Okay, we did many reactions with tertiary butyl nitrate. That's very good. And then this palladium catalyst, one for dioxane, 90 degree, 20 hour time. In this condition, you can get this. Nice reaction. And we get many examples here. If you look at the thing, whenever you do some reaction, you always substrate scope with different substituents. If you look at this unsubstituted, this is a substitute here substitution. So we vary the substituents everywhere and get all the where is get very good examples. Okay. And if you look at some unsymmetrical azoarenes, that was all symmetrical azoarenes. If you look at unsymmetrical azoarenes, this and this, then what happens? In that case, we found that even in this case, nitration occurs exclusively at this position. If you look at this, no, because this position also activated. Okay. But if you take this slightly vary the substituent here, then this is a very nice example that here you can get most of the thing activation here. If you look at the thing, this is the predominant product, this is the minor product. So the activation, you can change the activation at the position. That's why I told you, you can get activation ortho position, you can get meta position, you can para position. That depends upon your directing group and how you are using their metal and things. So here also, that's a substrate, you can get this activation here. Okay, fine. Okay, the mechanism is very simple, standard mechanism that the main thing of this CH activation is making the metallocycle. Anything azoarene with palladium 2, it can force this. This is called palladacycle or metallocycle. And this we have tertiary butyl nitrite. So it gives, under reaction condition, gives nitro radical, NO radical, then NO2 radical with here. This radical interacts with this, forming this thing with the palladium 3. Palladium 2, this is palladium 3. And this again on aerial oxidation with loss of electron, you can get palladium 4. And that it can give the product with elimination. So that's the standard thing. It's no problem. And here the palladium 3, we can get this evidence of palladium 3 by monitoring the reaction on UV. This is before reaction, you can palladium 2 here. But when the reaction is monitored, we found that palladium 3 is 445 the peak for the palladium 3. So we have the evidence of palladium 3 in the reaction, the reaction intermediate. Okay. Now, so this reaction again is mild conditions, avoiding use of metal nitride, applicable to wide range. Really, we have many examples, excellent regioselectivity, the additive and external oxygen free, high yield of products. Okay. We have a similar example, another example from our lab. The same azoadine, but we get acylation. We did it with some ketone, we can get the acylation here. Okay, and okay, some representative examples. Again, if you look at the things, that's very high yield of all the products. And this again we varied the substituents here, methyl, OMe, and here also methyl. So all the things you can get hetero acyl group. So we have got many more examples of that. Okay, okay. And by application of this protocol, we have also made this compound, but simple way on 2 steps method, you can get this compound. That's a liver receptor agonist. So that's a really an application of many methods. Okay. Okay, mechanism is almost the same. This is all the standard mechanism that is palladium, it forms this palladium cycle. And then this ketone, this TBHP oxidation, it comes, this is known. And then again, it can give this radical. This radical then reacts with, interacts with this, forming this, and by reductive elimination, you can get this compound. That's a standard mechanism. Okay. And also, it can also the applicable to introduce acyl, heteroaryl. So it's a very general method for any acyl moiety there. Applicable to a wide range of substituted azoadines, excellent regioselectivity, high yield of products, and also synthesis of this. Okay, fine. Now coming the real point, that what I am going to tell, that implementation. So after showing you the 2 examples by my lab or many labs, you can see that everybody is using palladium and also very high temperature in toluene, this type of solvent, maybe other, that is the usual thing. So serious, if you look at this with the green eye, you find that a serious drawback is that use of expensive and toxic metals like palladium, which I don't like. Okay, use of high temperature, again we don't like. And require another thing, very thing, requirement of introduction of a directing group. Once you have the directing group, there's a natural removal it. So that's another taboo. That you need a directing group, like a pre-functionalization, and you need to remove it. So that's the thing. If you look at the principle of green chemistry, that as far as possible, protection, reproduction should be avoided, right? So you're also like that you are introducing a group, directing group, and then you are removing it. Okay. So that's also again not on the green. Okay. And then solvent toxicity. Okay. And then selectivity. So all these things I will address, but may not be that like this, everything can be ideal. I'm not telling. Again, I'm telling from the green chemistry thing. When someone says that, yeah, you use, this is not green. Fine. You can change one parameter to a green, that's also green. Then in the next step, change the second parameter. But don't stop your efforts. Okay. So here also, I will address now the first 2 things. This palladium and high temperature. Okay. So our next move is that in this one, where is the C4 functionalization of 8-aminoquinolone benzamide here. This molecule, here also, if you look at the things, there are this position may be activated, this position may be active position, this one is active position, and C7 is active position. So here we found that when we did this reaction with an cyclic ether, tetrahydrofuran or so, with irradiation by a CFL lamp or LED lamp, with cobalt catalyst, look at the thing, we changed from palladium to cobalt, that's our objective. With the cobalt catalyst, at room temperature, which again we change the address the temperature, high temperature, room temperature, we can get very successful at position. This is the activation, this is got the functionalization, alkyl functionalization, and the ether. Real reaction is, if you look at the things, this reaction is cobalt external acetylate, eosin Y catalyst, tricyclic hydrogen peroxide, cesium carbonate, deimmersion, this CFL lamp or LED. This condition, you can, even in sunlight this reaction goes, but yield is not that good. We tried. Okay. So here, again it depends on the instance of sunlight anyway. So we can get this compound here where we addressed the temperature and catalyst. Okay, fine. That's a very nice reaction. And if you look at the thing, why you choose quinoline, quinoline molecule is a high important it is for chloroquine and many anti-malarial drug. And this tetrahydrofuran derivatives also, they have many pharmaceutical uses, all these things see. So in our molecule, we will have the potential to be pharmaceutically active. Okay. If you look at the thing now, when you look at the literature of the 8-aminoquinoline benzylamide activation, almost all that, whatever they have, very few reactions, all that things in the C5. Activation occurs at C5 with nickel, palladium, copper, iron and silver. We will not get any example of C4, where we got in C4. One example with C4 functional silver salt and the phosphorylation, you can get this one. But in our case, we got exclusively C4 functionalization. So you'd like to dig it, that why and how, explain it. Okay. First substrate, first chemistry. So because you have the result, then you can explain. So we found that that's a very general reaction for any kind of amide, variation in amide. We either change the substitution of the amides. You can get this, if this one phenyl, now this thiophene, alkyl chain, this bicyclic chain, everywhere, whether they change the amide, the reaction goes uniformly. We take the ether, variation of ether, not only tetrahydrofuran, 6-membered, that is the oxane, dioxane, and this, all the case, even in the acyclic case, you get the very good deal of this product. So that's a very general uniform reaction for CH activation at the fourth position by cyclic ether. Okay. Now for the mechanism and things. Bring some water. Okay. Now what? For any reaction, as you know, we know that whether radical or is this. So radical, we did this radical quenching experiment like standard thing with reaction to tempo, and we found that tempo completely arrests the reaction. Presence of tempo completely arrests the reaction. And we isolated this one, so that proves the reaction is going by radical process. Okay, fine. Thank you. Okay. So that is the radical reaction is going by radical. Then like all other chemists, we did the kinetic isotope experiment. As I told you, that we have to always learn, that Milan was telling that we have to learn all the things, this. So that is the thing. When you started my research, I did not know the kinetic experiment, we don't know the XPS, we have never heard of names, nothing. But slowly we just learned it because survival we have, for work we have to. So the kinetic experiment also I did not know those days, and we can do it. So when we did the kinetic isotope experiment, we found that Kh by Kd 3.7:1. That shows that the radical formation of tetrahydrofuran is a determining step. Okay. Now, again, we found a paper in literature where they calculated the C2, C4, C5 and C7 positions, their charge and their nucleophilicity, electrophilicity, and they found by natural charge distribution and PZ orbital occupancy, what they found that C5 and C7 may be the most likely electrophilic reactive site, and C4 and C2 is the most electrophilic in nature but likely the most nucleophilic reactive site. Now, whenever you have a THF radical, that's the nucleophilic in nature. So naturally, that will interact preferably with C2 or C4. C2 being little adjacent to this steric effect, C4 they prefer to. So we got exclusively the product at the C4. So that's called remote C4 functionalization, remote CH activation. That's also very hot. Okay. So the reaction pathway are almost the same. If you have that 8-aminoquinoline amide with cobalt, then found this first funding cobalt cycle or parallel metal cycle. Then from tertiary metal hydroxide on the reaction condition gives tertiary radical, which abstracts hydrogen from THF giving this radical. This radical then reacts with this, forming this radical. This reaction then one electron loss, you can get this molecule, and this one electric elimination, you can get the product. So that's all standard, and we have all the evidence also. Okay. So here, what I want to tell, that's instead of palladium, we call cobalt catalyzed selective remote C4 functionalization under simple irradiation of a CFR room temperature. That we addressed. Okay. And using cheap environment friendly eosin-wise catalyst, broad substrate scope, and mechanistic investigation, all the things. Okay. I will give another example from my lab with alternative of palladium catalyst. That's with copper. And these are now very hot that if you can do CH activation like copper, iron or so, that's very really good. So here one example of the copper acetate. Here this molecule again, that's 8-aminoquinol benzamide. Here when it did this with azide, acyl azide, in presence of copper acetate, again room temperature, we can get this benzoyl amide. Okay, that's benzoyl amide. Okay, but very nice here that the student, this work was done by Tubai and Pinto was the senior author. Then Tubai was new. So what he tried the same reaction. When he tried, he did some more amount of copper acetate. That's usually happened when you are giving some catalyst some more amount. So when a more amount of copper acetate, then we cannot reproduce the NMR with this. We got a new compound. When we analyzed, we found that we got another compound, not benzoyl azide, we got acyl azide, acetyl azide. How that is possible? That's a different thing. Then first generalize. So what we then found that when we use copper acetate 1.2 equivalent, always get, this is the major isomer, benzoyl azide. But when you use 2 equivalent of copper acetate, same condition, everything same, only we change the loading of copper acetate, we got acetyl azide. And we got that via this. I will come to the mechanism. So first, just let us generalize the result. We found that yes, really with 1.2 and everywhere, all the time we got that is the major product and that is minor. Okay. If you look at the things, all the substrates very high yield and this. When we get the 2 point, look at the thing. We did not change anything. Just we change the loading of catalyst 2 equivalent and we get the major product now is acetyl azide. Nice. I mean, interestingly, very interesting, very nice result. And always chemists, when you get some unusual thing, they're happy. So happy in that way. Okay. So we got the minor product. And so we developed 2 methods to give acetyl azide and benzoyl azide. A simple reaction. Okay. Now, what is the mechanism? Why it comes from? Okay. Then we found that whether it is coming from acetyl, whether some way the acetyl azide is formed. So we did a commercial acetyl azide with this reaction. We found yes, the product is formed. Then how that acetyl azide is coming? To know that, we did another experiment. We took benzoyl azide. Whatever the reagent, we used benzoyl azide and quinolamide, nothing else. So we took benzoyl azide, same condition, copper acetate 2 equivalent and all the things. Here we found from this reaction we are isolating acetyl azide. That means acetyl azide is coming from the reaction of benzoyl azide and copper acetate when it is 2 equivalent. Looked at the literature. We found that yes, copper acetate can release acetate ion. There are many examples. So here happens that copper acetate, acetyl moiety is coming from copper acetate reacting with this and we can get acetyl azide. Okay. Then we get another experiment where we get the same reaction with a mixture of acetyl azide and benzoyl azide. The major product then comes from corresponding acetylamide. That means the product is coming from this and this. You can get a trace of this. Okay. So that proves our hypothesis. Okay. Mechanism is same standard mechanism that this with copper from this cycle and then detected by we found that this and then reacts with the acetyl azide, you can get this, the normal mechanism. Okay, I'm not elaborating this because I have another thing. Okay. How much time I have? Yeah, okay, fine. No problem then. Relaxed. Okay. So here one thing, the main thing what I'm address, that's the question of many people, that whether we can avoid introduction of diet group. So what we thought in a way, that whether the diet in situ, you choose some substrate where you can get the dietary group in situ. We are not using it. We are not pre-functionalized or anything. In situ. And that direct product is involved in the reaction. So there is no need of removal of dietary group. And also selectivity. Selectivity is a point for many, many years about the CH activation. So we address these 2 points and okay, let us look at the thing. So what we thought, just is thinking, we thought that if we chose this substrate, that is benzoxagenone, and this is known with cesium carbonate hydrolysis, it can get this molecule. Now if you look at this molecule, that's the directing group, and that's also, somewhat directing group. So what we thought, instead of cesium carbonate, if we do this reaction with nucleophile like amine, some amine, benzyl amine or aniline or whatever, some amine that can react with this and can form this type of compound. That is coming from this part and this is coming from this part. This. If you look at the molecule now, so you have 2 directing group for CH activation. It can activate this position or it can activate this position, right? Or it can activate this position, okay? So real example when I do it. So we take the benzoxagenone, aniline and diphenylacetylene, and then in ruthenium catalyst, again, no question of palladium, ruthenium catalyst, we can get very good high yield of this product, solid product, high yield of this product. So from this thing in one pot, in this, you can get this product. And here, if you look at the intermediate is this one, okay? So it can, with ruthenium, it can form this ruthenium cycle, activating this position. With ruthenium cycle, activating this position. Or with this, it can be this position. But we got only selective activation at this position, we got this compound, okay? So what actually the reaction involves, nucleophilic addition of amines to benzoxagenone followed by disubstituted alkyne addition controlled by an in situ generated amide center. That's very important. The reaction is controlled by in situ generated amide center. That means directing group is in situ generated and that is controlling the position. I will come very interesting result. Actually this reaction, when my last student Shubir left in 2020, only this work was not complete. All other works I published. So he just go like this. And then after a few years, he did postdoc and all the things. Last year in October, we have always communication. He said that, sir, I completed that work and I am sending you the write-up. Look at it. I said, that very good. It's okay. It looks very good. I assigned some other works. And then this work came and was so happy that this is another thing, I'm lucky to get very good students. That student left in 2020, but still he did not get this work, just remain like that. So did the work in a postdoc sometimes, take 4 hours, is fine, 4 years, fine. Then he completed the work and this is a good step. So that okay. So this reaction now, only this, okay. So here I will explain more that how this reaction should work. Okay, so real work that this one, we can this condition of the real condition here, phenylacetylene, then this ruthenium catalyst commercially available, copper acetate, and this you can get toluene, that's a non-toxic solvent, you can get this product. Very high yield of all the things. Okay. And here, when you look at the literature, if you look at the ruthenium catalyst, by change of the catalyst, you can change the position of activation. Catalyst, the functionalization occurs here. Okay. When we change this catalyst here, the functionalization occurs. That's the control side selectivity. Our motto is that substrate selectivity. We haven't just substrate, this substrate, catalyst same. So this substrate, we can control the high selectivity. We can control the CH functionalization. So it's the substrate control side selectivity. Component knowledge and cascade annihilation reaction. And okay, and with that, with optimization, we found that is the right condition. Already I said. And here, if you look at the things that always vary substituents here, we have what you can vary. You can vary the substituent here. We did it. You can vary the substituent here. You can change the amine. You can change the acetylene. So we did all the things here. We change the substituents here. This group and this group, you can find that all the proof of X-ray also. is a substituent, here is substituent, here is a different substituent CF3, here is a different substituent. We have all the examples that where we can change the reaction very well. Now, okay, change the amine, not only aniline, you can get any kind of aniline, benzylamine, alkylamine, any kind of amine, then you can get a similar result. Here we have the, then we have, yeah, ethylamine, butylamine. Change. Look at the change of substrate, the amine position. This one, this long chain amine. Okay, even hydrogen. Okay, so phenyl hydrogen here. So all any kind of amine, that is heterocyclic amine, any kind of amine you take, the reaction goes very well. So that's okay. Our next thing is that what about changing the alkyne? Instead of symmetrical alkyne, we take this symmetrical alkyne. We started diphenylacetylene, then dithydacetylene, di-N-propylacetylene, there is diaridacetylene, this heteroacetylene, and then that is unsymmetrical acetylene, this and this. And there we found that again the reaction goes very well. And here very nice example. Vinyl methyl acetylene when you take, we got only product is only this product, methyl here. Okay. And again we take another example, butyl phenyl, that's also the activation is here. So that means the electronic regions, phenyl will come here, we can get this one. So that's all, we have proof of X-ray. So that's the thing that we varied all the parameters. Okay. Most important part of activity. Like all our synthetic method, we got gram scale experiment, we got a very good similar result. Here the compound can be utilized for making a drug. Is this? That's inhibitors of certain protease. This is one thing. When you have this compound, means are very powerful. Hydrolyze this thing easily. Wait. And this thing, very important thing here. But we have a methyl position here, methyl substituent here, and do the same reaction, same condition, we got only the intermediate. No annulation here. No annulation here. What does it mean? That means it is exclusively side. If your side position is blocked, if your this position is blocked, no reaction occurs, no annulation works. So that means highly, exclusively side selective substrate. So that is called, we call substrate, what we like to acquire, the substrate side selectivity at this position and no product formed here. Fine. And then intermediate we got for this. When we did the two-step reaction with amine, we got this compound isolated nicely. And then second step we reacted with acetylene, we got this compound. So that is the intermediate of this thing. So that's easy to now speculate the mechanism. So we got that, before that again we did some DFT study. As you looked at this, when you look at the thing with ruthenium, it can be 3 cycles, that this position can be activated, this position can be activated, and this position can be activated. So we make the 3 cycles, and this is a 6 stable, so we considered B and C. And when we do the DFT calculation of these intermediates, we found that the cycle B is more stable by 21.6 kilocalorie than thing. So which also matches with our experiments, that this cycle, that means this is more energy favorable, so reaction annulation occurs at this position, we get this compound. Okay. So mechanism is almost the same. So when you get that benzoxagenone with diacetamine, you can get this compound, and this your intermediate, and this with ruthenium from this cycle, and from that with alkylene you can this ruthenium addition, then 1,2 insertion, you can get this compound, that's all known. Then by reductive elimination you get this product. So mechanism you can get this product. And really we are happy that what we tried to achieve, we achieved in this way, that no need of directing group, no removal of directing group, and you get exclusive site selectivity. Okay. And if you allow me, I will give one example. That's okay. This one is, okay, we can say highlights this use of inexpensive and non-toxic ruthenium compound as catalyst. use of non-toxic solvent to alveolar rejection medium, no pre-introduction of reaction group, exclusive site selectivity. And very nice thing here, if you look at the reaction, there is a regioselective construction of new CN bonds through in one step cleavage of CC, NH and CO. One step you are cleaving 3 bonds and making 2 bonds. That is in one step without thing. Okay, so that's thing in chemistry wise. Okay, I will come one example. That's like a CH activation. That's by technique. That as I told you that directing group, this and all the things, metal. So here without any metal, without anything, if you look at this type of molecule, that's simple butanephthyl. Here you can get with selenation diphenyl glycinide or other selenium halide or so. You can get with ball milling, you can get the selenation at this position. That's why CH activation here. You can get this compound. You can get this compound. So that's again ball milling is very much coming in. The first example gave a Custom bomb. That's by ball milling in mechanochemistry without any other room temperature. At this you can get the successful CH activation. Okay. Now many papers are coming. Many papers are coming on CH activation under ball milling. Okay. Now we have many examples here. So I think this everywhere we got the nice product. Okay. Okay. That's nothing. Selenation, selenium sources. Okay. Okay. Yeah, we get gram scale synthesis, reaction tempo, no effects. So it is going by ionic mechanism, normal mechanism. With the weights, you can get this thing with base, and this is financial normal mechanism. You can get this compound. So nothing else. Okay. Okay, and then again, I'm telling, acknowledging my students. I'm really lucky to get all my students are very, very good. And this is Sabir, Devashish, Pintu, Biju, Tubai, Sabir, all are now employed in somewhere in academic positions or so. And also for fund, I got my Indian National Science Academy as a senior scientist, JC was National Fellowship, of course, my institute. And finally, I thank you. Okay.
Now the platform is open for questions.
It's okay? Time is okay? Okay, fine. Okay.
How much maximum amount can be done ball milling?
Okay. Yeah, I can hear. It depends upon your ball milling. The lab ball milling, what we have, it can give maximum 500 milligram. But whatever I saw in Germany, I visited Germany, one of my colleague, co-colleague Akim Story is there. When I started work with him, the book was written with him. So there, when I visited, I saw he took me to the industry. So those industries, they have built up a very big ball milling apparatus. Not that big loop like factory type things. There you can do kg, 1 kg, 2 kg. In one step, they can make the method. You can do it, no problem.
Here, 500?
Yeah, 500 milligram. Yeah. With the apparatus we have, most of the apparatus like this. I have race apart Germany, from Germany made race. That one very popular one. RETSCH. Gram scale will be a little difficult. Depend upon the reaction again. Yeah. It depends upon the jar. What jar you have. If you have a bigger jar, you can get maybe 1 gram. Yeah.
Okay, thank you, sir. I have shown you have shown most of the reaction. We have also do like this of reaction, like click chemistry. We have done same time, and circulations. We have same fields. So we are also working with Evelina and others. This is very interesting.
Yeah. Okay, students. Okay, if you have any questions or anything, just you can ask me. No problem.
Sir, wonderful lecture. Just I have 2 questions.
Sure.
One is you have used cobalt. That is an expensive metal.
Cobalt acetate is not that expensive.
Okay.
It depends upon the what. Cobalt iodide is very expensive.
The cobalt metal itself is an
So
salt. So
10 more percent.
you mentioned in the beginning that
expensive. Definitely. If you can do ruthenium, that is very good. That's less costly. Yeah.
And another point is you are mentioning many times about the ball milling. When you do ball milling, there is a local heating is generated.
Not much. We measure the temperature sensor. It's not more than 40-45 degree temperature.
But there are reports for nanomaterial synthesis, even in the local temperatures, when two balls are colliding, in between that 1500 degrees centigrade is also generated. So how do you?
But it does not show when we put the sensor in the inside the reaction medium. It does not show more than 45
No,
degrees.
I'm not talking about inside the chamber.
Yeah.
I'm talking about this
Yeah,
ball and this
maybe,
ball.
might be. Yeah.
Inside, in between the
in
two
between,
balls.
yeah, right, yeah.
This is a technique where interface, that local temperature is generated, and that temperature we use for even melting also can happen.
Okay, I understand. Yeah, but that does not affect the reaction. Whenever you do the reaction, doesn't affect. Maybe that's true. Yeah.
Okay. Yeah, this is in metallurgy. It is a very common.
Yes, okay. But if we do the reaction, there is a grinder. That's one of the auxiliary. That's also alumina or sand or whatever. So that might absorb or something. I don't know exactly real what is going on.
Okay.
But the reaction is not affected in that way. Yeah.
Okay. Thank you.
Yeah, sure.
Thank you, sir, for the lecture. So, in the ruthenium catalyst reaction, you used primary amines. So, if we use secondary amines, what will be the fate of
We have not and go. Secondary will go. Tertiary naturally will not go. Secondary will, I think, no problem.
Okay.
We have used primary amine. That's true. Yeah.
Thank you, sir.
Yeah. Sure. Get the mic. See there. Okay.
Depends of maybe and amine derivatives. So I wanted to ask you, were there any significant electronic effects from amine substituent that influence the reaction?
No. Say it again. I cannot hear. Yeah. Okay.
Hello.
Yeah. Only the question.
Sir, I actually wanted to ask you that you have given excellent yields with benzoxazines and amine derivatives. So were there any significant electronic effects that were maybe affecting the yield?
Yeah, I tried all possible substituents here in everywhere. This electron donating, electron withdrawing, and all the things. Almost the uniform. Some change in electron withdrawing group, but almost uniform. Yeah.
And so one more thing that you have in that OL 2025 paper, there are two catalysts, maybe ruthenium and copper together.
Oh, yeah, that's earlier. Yeah,
Copper
okay.
is only acting as an oxidant or is having some effects with amine derivative or something.
Yeah. That's the ruthenium different. I showed it from literature. That's with ruthenium, catalyst controlled. If you use different catalyst of different compounds of ruthenium, it can control the site selectivity. That's what I showed. And there are other examples also. That is not the only example.
And so one more thing, in the first reaction that you have given, the triazole reaction, you have written specifically 600 RPM in 6 balls. Were there any role of it?
Yeah, that's okay. The one thing that you have to, by error and trial, you have to find out that which RPM is giving good yield. You can 800, you can 1200, whatever you have in your instrument you have. But then that you have to find out that which one giving you good things. Yeah.
So one more thing, you have written purification with ethanol. It is a kind of precipitation or column chromatography.
No.
Because it's like a little bit difficult to control ethanol.
Okay, I'm telling you, when you are just let's say compound, wash with ethanol. Evaporate the ethanol. And when this is concentrated, just keep it in your table. You will get nice crystal.
So it is a single spot kind of reaction, sir?
Yes, that's a very nice reaction. Nice in the click chemistry reaction.
Thank you very much.
Okay, sure. Sure. Yeah. But other people will not hear.
That's basically environmental microbiologist. So I just have a curiosity.
Sure.
Views. I just want to considering real chemistry, I think. So can we use any enzyme specifically to make the code greater?
Yes, definitely. Yeah.
Chart solvent.
Yeah, there are many examples that where using enzyme you can get a better yield than this synthetic catalyst or so. There are many, and that's very much in the purview of green chemistry. As what I told you, that's the article I told you, that's Chemistry International, where it shows that using enzyme, the reaction goes, how good the reaction, enhances selectivity, all the things can be controlled by the enzymes. Yeah. There are many examples. Many people are working on that field. Sure. If you look at this, I'm taking one example, that carrot root, carrot. If you look at chopped up the carrot, I showed it in the, demonstrated that in a practical class. The carrot root, that can give very good enantiomeric reduction. If you took an alcohol, acetone or so, you can get the very enantiomeric alcohol. Carrot, just carrot root. So there are many examples like that, yeah, sure. Enzymes, pig liver and all the things, many examples, sure. Yeah, sure. Yeah, sure. Triazole moiety. Catalyst, right.
We have copper as a heterogeneous catalyst.
Yes.
So when that recycle, yes, I should use the heterogeneous catalyst. Maybe at this catalyst, we have prepared.
People, yes.
So while we prepare the heterogeneous catalyst, some characterization is
Everything done, yeah.
so some money is lost.
Money is
Can
lost.
we use simply copper or aluminum?
Okay, I'm telling you that copper alumina compound copper, we used it from copper sulfate and alumina. Copper sulfate is very, very cheap. Alumina is very, very cheap. Just in water, we dissolve copper sulfate in water, add alumina, stir it, and then remove the water. How costly it is. You get copper sulfate on alumina, solid, and that's alumina. If you wash with water, that copper will not go. That's anchored on that. Okay, I'm telling you. That catalyst I used here, and you can recycle it for 12 times, 15 times. So, okay.
Just benefit
Heterogeneous recyclability and a very inexpensive catalyst.
But can you use simple copper salt? Or
Yes, then you can recycle. Then you cannot recycle. My objective, exactly, my objective is to that minimize the cost and recyclability, sustainability. Okay.
The role of copper is
Oh, that's the basic thing of that's a click reaction with copper. Yeah. Now, catalysis by copper in the click reaction, that's known, well known. That's well known. If you look at the thing, any book, anything, you'll know. You look at the book on the click reaction. I'm not telling you. Then you'll find out. Okay, sure. You have questions? Yeah.
If we use like copper and alumina, the solution
Definitely.
before,
Yeah.
or the heterogeneous, I think the yield will be more in the homogeneous case. What do you think?
What can be the more than that? We have got 99% yield also. Okay. No. One thing I'm telling you. Okay. If you use the homogeneous solution, then you can use the ball milling. That's the problem. Ball milling without solvent, without thing, solid dry thing, you can use the surface. Okay. For ball milling liquid, there is the liquid as a grinding. That's a different ball miller, which I don't have. That will do. So in that way, I have to use without solvent. Okay. And that catalyst is very nice catalyst, solid catalyst. Just add your compound, all three compounds, add to that. Start the switch on. That's all. Any technician and school student can do it. Put benzyl halide, put sodium azide. You not took it, that's why the gloves use the sodium azide. And then use some alkyne, okay, on the same thing. Just when this, start the switch on. Wait for 30 minutes or whatever necessary, then you can get the compound. And then wash with ethanol. So very, very nice method, and they get the crystal of the compound. Most of the things, because it's two aromatic compounds, so you will get the very crystal of compounds. That's a very nice thing. That's I told you, one of the easiest method of making triazole by this method. The only thing you have to use is ball milling. So yeah.
Sir, one more thing.
Yeah.
For this copper acetic catalyst addition reaction, that benzoyl azide kind of things, and then copper acetate has been used for that reaction. And when we are using more equivalent of copper acetate, then methylamide is and for that reaction, you have shown that whatever the nitrite changing happening with benzoyl chloride with copper acetate and corresponding CH3CONH radical is performed. But in that case, let's say, can you use simple copper acetate and simple sodium azide? Because then it is possible to generate this CH3CONH radical.
Yeah. Yes. Okay. That's the
That
same.
also possible.
Yeah, that's possible. Same thing. That's known.
That is already
Known.
before
Yes.
that.
I'm not. We are not using sodium azide here.
Just only this.
Only these things here. Okay.
Okay.
It's coming from acetate, copper acetate.
That
Yeah.
coming from
Yeah.
copper.
That's known. Yeah.
Okay.
Sure. No. Absolutely no. Because acetate is a component of that. We use copper chloride. In the paper you have written copper chloride, copper iodide, or whatever, but nothing works. Only thing that copper chloride and acetic acid, that works. But without copper acetate, the reaction cannot go. OTF, we have not used it, but yeah, OTF maybe first reaction might go on theoretically. I'm telling, yeah, but they're very costly. OTF is very costly in acetate. Why I'm going to think of OTF? Yeah. Sure. Yeah, because the same type of, yeah. I don't know. I have not tried. Definitely not. But electrochemical based CH activation already, I think, is explored now. Yeah.
Nowadays, Dr. Ackerman is.
Yeah. Ackerman is doing. That's what I'm telling. But I have not. I don't have electronic device.
Okay, because that is one of the route nowadays people are doing. Another thing, sir, ionic liquids. Did you
Yeah.
try?
I am.
Because today we
I
did
first
not
started
try.
ionic liquid in India.
Yes.
Anyway, yeah. What do you say? What is the question?
Ionic liquids because they have low vapor pressure.
Yeah.
So, that kind of reaction.
Yes, ionic liquid can do it. Ionic liquid is a catalyst and solvent is very nice.
And biomass derived some of the
Yeah.
solvents also.
Definitely. Yeah. Not very expensive. Depends
Not
upon
that
if I always make in the lab. I have not buy it. One thing, but iron liquid, the problem with the iron liquid, many of the liquids are toxic.
Toxicity.
It was abundant. Or people have, not doing that emphasis on research because it's toxic. Nothing else. But it works very fine. Very fine. A lot of people iron liquid. Yes, and sometimes I was called iron liquid man. When I went to Korea in an Indo-Korean delegation, that time I talked about iron liquid, and after the lecture, many Korean people they say, "Hey, iron liquid professor."
Any more questions?
Yeah.
Thank you so much, Professor Ranu sir, because you have given an excellent presentation for a long time. And hats off to you that you are giving such good presentation at this age. Thank you so much. That is worth mentioning. So now it is the time that faculties please come forward so that we can felicitate him. It's a big honor for us.
No problem. So long as health permits, I'm fine. Okay. Oh. Okay.
That person who asked about biocatalyst recently has received Industries. Indo-Russian. Yeah, he's also MSc from North Bengal, followed by PhD in Professor Khare.
Oh.
That's why he asked that biocatalyst. This is the handmade by our staff.
Thank you. Looks like it's okay.
Yeah.
Sure. Very good. Handmade is always good. Always.
This is a big honor for me.
Honor for me too. Definitely. It's fine.
Please, that's it.
It says.
Okay, thank you. Thank you all. Oh, so many things. What we have done. Another one. Okay. Let's have a group photo. Why so many? Yeah, sure.
एक group photo ले ले.
Why so many things, huh?
There's another thing, we'll give you.
Another thing. Okay. One is fine. That is all.
Yeah, this is done by Mr. Vikas.
No, that is fine. Okay.
Another should be. From the light. Light को switch on कर दीजिए.
On the line.
Let us proceed towards lunch. And Mr. Vikas, carry all these things to the department. So that we will like to invite you. There is a PhD Viva today, and Mr. Suman, the first student of Debolina, will be presenting.
Sure.
So we would request you if you can also be.
Yeah, no problem. I don't have to.
He's working in that CH activation.
Oh,
That's right.
Selenium, she's using the last work which you showed is Selenium. All are Selenium.
नहीं ये मेरे ग्रुप के साथ एक उसको इसमें आपको
पीछे से लेने से जब तक तक
ऑर्गेनिक
all organic.
ये फोटो ले
अच्छा अच्छा, so sir can sit here so that all students will be there. I think that's important. Sir, please. Sir can sit here. We all will stand. Sir, you can sit. Yeah, we all will be standing. कैसे ही? आप लोग बच्चे? Stay there. Stay there.